Hello everyone, and welcome to the Thin Film Applications webinar. For those of you that don't know me, my name is Chris Wagner, and I'm one of the product engineers here at East Syracuse, New York for the Thin Film product line. I'll be leading this webinar, and Sheldon Wayman will assist with the question section at the end. Please feel free to add your questions to the chat at any time, but know that your questions will not be answered until we reach the end. Thank you for attending, and I hope you enjoy this webinar. Here's a quick look at what we'll be discussing today. We will first have an introduction to Inficon ISS to give an idea as to where we are located, what we provide, and some exciting innovations that we've made to our location. We will then have a small refresher on quartz crystal microbalances, also known as QCMs. In this section, we will cover what a thin film is, why QCMs are important when producing thin films, and an overview of how QCMs are used to make products you are familiar with. Next, we will look at how thin films are applied to a product. In this section, we will discover different ways to deposit a thin film, how a thin film is applied to an object, and what QCM we would recommend for a given application. We will then cover some of what makes each method of depositing a thin film unique. At this point, you'll be ready to look at some products that have thin films. In this section, we will see different products that have thin films, and we will provide some top-level information about the deposited films. Lastly, we'll have a short recap on some key takeaways we hope that you walk away with today, followed by some upcoming events. Now let's get started with what Inficon ISS is and where we are located. The ISS in Inficon ISS stands for Intelligent Sensor Solutions. East Syracuse, New York is the main location for R&D, product management, and manufacturing of the ISS product line, while our QCM crystals are manufactured in Overland Park, Kansas. We also have 2 locations in the US where our intelligent manufacturing software is developed, known as IMS. Those locations are Boston, Massachusetts, and Austin, Texas. The images you see here are of our East Syracuse location, showing off our 100K and 10K cleanroom areas where our products are produced. For ISS, there are 5 main sets of products. You have thin film, sensor technology and control, known as STC, products for semi-OEMs, intelligent manufacturing systems, or IMS, and energy and security, known as ENS. When looking at thin film applications, we'll be focused on the thin film set of products, but keep in mind that many thin film applications will also have other sets of products from ISS. Here are some of the awesome innovations that we have made in the past couple years. First, there's the manufacturing and cleanroom expansion of 2016. The expansion greatly improved our capacity for production, and that's in the top left-hand corner. We also opened a collaboration center in 2019, and this space allows for more collaborative efforts between product lines, as well as a fantastic location for new product development and to show off our prototypes. Next is the ISS Minifab, which opened in 2020. The Minifab allows us to perform more application testing internally in order to develop the right sensor for many applications. And lastly, but not least, there is the lean manufacturing team who's able to provide the world-class delivery times by adjusting the market needs and improving production efficiency as a whole. Now that you've seen a little bit about Inficon ISS, let's get a quick refresher on QCMs. Before we take a look at thin film applications, it is important to understand what a thin film is. A thin film is a layer of material on some surface, similar to the candy coating of an M&M, except it's much thinner. In the upcoming application, the thin films can be anywhere between nanometers to micrometers in terms of thickness. In many practices, the thin film applied to a surface will consist of many different materials deposited in a sequential order. We will be referring to the surface that you want to coat in a thin film as a substrate through most of this webinar, as it's a generic term. However, keep in mind that for certain applications, there may be different names for the substrate, such as a wafer for semiconductor industries. A thin film is most commonly deposited onto a substrate using one of the applications we will cover in this webinar. The thin film is deposited differently depending on the application, but there are some things that all applications have in common. For example, the material you want to deposit onto the substrate always starts in some initial location. Depending on the application, this may be referred to as a source, a target, or something different. You may also have a substrate that you want to coat, and that substrate is in some type of a container where the coating would take place, and that can be referred to as a chamber. In all applications, the desired material has to travel some distance and then become deposited onto the substrate through either a physical or chemical change. In this example, we physically heat up the source until the material in the source either evaporates or sublimes. The newly gaseous material then expands to coat all of the cooled surfaces in the chamber. And then after the deposition is complete, you can see that a thin film has been deposited on both the substrate and the QCM, as shown by the blue marks on those two parts. In these applications, a QCM is an effective tool for measuring thin film thickness as a deposition takes place. This is known as an in situ measurement, and a QCM is able to provide in situ measurements of a thin film because the QCM sensor and the substrate are both coated by the source material at the same time. By using a QCM, you are able to ensure that the thin film will be the same thickness for all substrates used in production. This improves the production yield and the overall quality of your coatings compared to measuring thickness after the deposition has taken place, which that method would be known as some kind of an ex situ measurement. Our QCM systems are commonly used in PVD and CVD chambers in order to deposit thin films on key components used in final products you may be familiar with. In this example, we've got a touch screen that would be the key component, and it's coated in some kind of a thin film, and that could be found in something like a smartphone that you use on a day-to-day basis. We will take a look at several objects that you use on a day-to-day basis that require thin films, but let's first take a look at some different ways to deposit a thin film. In this next section, how thin films are applied to a product, all the tools shown are some of the tools that we use for testing various applications here at Inficon ISS. So the first method for depositing a thin film would be using resistive heating. In resistive heating, we pass a large current through a vessel containing a source material that is in a solid state. The vessel could be what's referred to as a boat, but it also could be a crucible or something as simple as a wire. And as the vessel heats up, the material in the boat eventually changes phase from a solid to a gas. The gas then coats the cooled surfaces in the chamber, such as the substrate, QCM sensor, and the chamber walls to form a thin film. Physically changing the material's phase in order to transport it from the source to substrate makes this a physical vapor deposition application, also known as PVD. One thing to keep in mind with resistive heating applications is that the substrate will be exposed to high temperatures. This can make the deposition with plastic or the deposition onto a plastic or other temperature-sensitive substrate more difficult. A QCM controller is a great addition to a resistive heating application as it allows you to control the deposition rate of the source by regulating the current that's passed through the boat. Any of our QCMs are ideal for use with a resistive heating application. An electron beam is a type of PVD application where electrons are emitted by a filament in what is called an electron beam gun. The emitted electrons are then arced around a permanent magnet until they collide with the source material in the crucible. This application evaporates a small area rapidly by effectively striking the source with lightning. You will commonly use an electron beam sweeper in order to move the beam inside the crucible and allow for an even melt and evaporation of material without drilling a hole into the source. It is important to note that the sweep pattern that you use on your electron beam sweeper will affect the spray of some materials. And this is most commonly seen with materials that sublime or that are known to have very directional evaporations or sublimations. As with resistive heating applications, a substrate is going to be exposed to high temperature, so that's something you'll need to keep in mind. And also, like resistive heating applications, a QCM is a great addition for an electron beam evaporation. Another common PVD application is sputtering. Sputtering is quite different than resistive heating or electron beam evaporation, as it doesn't heat the source material. Instead, a sputtering system bombards what is called a target with energetic ions. These energetic ions are formed by ionizing an inert gas into plasma, and then the plasma will strike the target, ejecting small pieces of the target towards the substrate. In sputtering applications, you can either deposit material onto a substrate or etch material away from a substrate. And when you're etching material away from a substrate, the substrate is actually the target. With sputtering applications not relying on a heated source material, the operation can take place at much lower temperatures. And this is where you're going to see a lot of those plastics and temperature sensitive substrates get used. A sputtering application may be required with a sputtering sensor if you're using a non-magnetron sputtering application. And that's because the electrons would hit the sensor otherwise, but with a sputtering sensor, which has a permanent magnet, it's able to deflect a lot of those incoming stray electrons. For magnetron sputtering applications, any QCM is going to work as the plasma is contained by the magnetic field and is kept away from the QCM sensor as a whole. A lesser known type of PVD application, yet one that's equally important, would be molecular beam epitaxy, or MBE. MBE systems are like resistive heating applications, except for a few key differences. So first, the boat's replaced with what's called an effusion cell, also known as a Knudsen cell, which is a long heated tube that houses a very small amount of material. MBE systems have a high amount of temperature control of the source compared to resistive heating applications, thanks to heating this long tube versus a small crucible. And this high amount of temperature control allows the deposition rates to be run at a very low rate and actually build layers one monolayer at a time. With layers forming at such low rates, you're actually able to achieve what's called epitaxial growth, which is where the material that's deposited is actually forming a crystalline structure, which allows for great uniformity and directional depositions. In order to achieve low deposition rates, MBE systems require operation in what's called ultra-high vacuum environments. Any pressure between 10 to the negative 10 and 10 to the negative 12 torr is considered an ultra-high vacuum. Getting a chamber to reach an ultra-high vacuum can take days to achieve, which means that MBE systems prefer to have as much time between breaking vacuum to atmosphere as possible. With this in mind, using a rotary sensor can be a suitable option for this application. And another option would be what's called a guardian controller, which uses electron impact emission spectroscopy, or EIES, to determine the deposition rate of monoatomic species. You might be wondering when you might need epitaxial growth for your thin films. Well, MBE systems are a key component for manufacturing magnetic sensors and infrared sensors that operate at room temperature without water cooling. Some examples of end products that need MBE systems would be the magnetic sensors in your phone, which allow you to use it as a compass. And MBE systems are also used to make infrared sensors, such as those that detect drafts in your room, as well as see warm bodies in an area. With that in mind, it becomes more clear as to why MBE systems are important. Moving away from PVD applications, we take a look at chemical vapor deposition, or CVD. This is far different than the previous applications we've mentioned, as CVD goes about depositing the desired material onto the substrate through chemical reactions instead of physical changes. In these applications, precursors and other reactants are delivered to the chamber via inert carrier gases. The reactants and precursors then react on all surfaces of the chamber, depositing the desired material that previously was part of the precursor. CVD applications have a tendency to be very time-based, so long as the flow of gas into the chamber, as well as the concentration of precursors and reactants in the carrier gases, remains constant. Because of this, QCMs are not always considered for monitoring the deposition rate and thickness of CVD applications. However, QCMs are proving to be more valuable in these applications to monitor other things, such as verifying precursors passed through the chamber, verifying that chamber clean endpoints have been reached, and also for providing other data points to ensure chamber stability. In these situations, a type of semi-QCM sensor is recommended to be used together with FabGuard. And the CVD chamber used in the lab has been named Darth Vapor, as you can see here, which was the winning name from a chamber naming competition. This chamber is one of the many in our mini fab. Atomic layer deposition, or ALD, is a type of CVD application with some key differences as to how the reaction takes place. For CVD, all precursors and reactants are added to the chamber at once, while ALD goes through a sequence of precursors in order to deposit the desired film. The sequence is usually a 1-2-1-2 style deposition, but the sequence is often larger than 2 cycles. ALD systems are used to deposit one monolayer at a time in a very controlled deposition. However, chemical reactions are very temperature dependent, and the substrate must be kept at a set temperature for the deposition to take place. Depending on the deposition, the substrate may need to be kept at a very high temperature. QCMs are less often used for ALD only because the thickness is heavily controlled by how many cycles of precursor have passed through the chamber. However, QCMs can verify if enough precursors passed through the chamber, as well as if any precursor has reached the chamber at all. In these situations, an ALD sensor is recommended because an ALD sensor uses temperature optimized crystals to ensure good rate and thickness measurements while water cooling isn't an option, and also has a backside purge where inert carrier gas can be purged into the sensor to greatly reduce material buildup inside. And here's an image of our ALD chamber that we have at Inficon ISS, and we've named this one Waldo, which was the winning name from the chamber naming competition, and it's also in the minifab. In the realm of research, thin film and QCMs play an important role in the development and study of materials deposited in liquid environments with new and unique properties. This is thanks to QCMs being inexpensive compared to X-ray diffraction, or XRD. Some liquid applications where a QCM is used would include electrochemistry, spin coating, and surface research. QCMs are even used in clean rooms to detect contamination. And QCMs operate in liquid applications, but you would need a 1-inch research crystal in that case, and you're going to need a special QCM controller for that 1-inch research crystal. Okay, that's it for the different ways to apply a thin film. Let's take a look at what products have thin films that you might be familiar with. So here's a small list of commercial products that have thin films in some part of their construction that you may be familiar with. By no means is this an exhaustive list, but instead it's a small taste of what's out there. The different products have been broken down into a few categories based on what type of thin films they contain, but several of these products can easily fit into 2 or more categories. We're going to touch on optical films, metallized coatings, metallurgical coatings, electroluminescent films, coatings used for energy collection and storage, as well as semiconductors. So let's dive in and see what we see. First, we have optical coatings, where multiple layer stacks of thin films are either evaporated or sputtered onto a lens, mirror, or prism. Optical films are used in order to control how much light is reflected, refracted, or what wavelength of light is allowed to be transmitted through the lens. There are large numbers of products you may be familiar with that have optical films. For example, the anti-scratch, anti-reflective, UV protection, anti-fog, and transition lens coatings on your glasses are prime examples of optical films at work. Similar coatings can also be found on high precision binoculars, telescopes, and rifle scopes. Thin films are also found on the lenses of your smartphone camera, which has a list of thin film coatings to improve the quality of the image being captured for like social media, family, and friends. And there's even optical filters which can only allow certain wavelengths of light to pass through, as well as dichroic prisms, which either are going to split white light into red, green, or blue, or more commonly are going to take red, green, and blue light signals and merge them into one full color image, which is seen on a few projectors. Another thin film would be metallized films, where there's a thin sheet of plastic that's typically coated in a thin layer of metal for decorative use or to provide some kind of function. Common metal coatings that are used in metallized films are going to be made of aluminum, chromium, nickel, or gold, but there are other materials that are used. In decorative coatings, the metallized film is there to just improve the appearance of the object by adding a high polished metallic film. However, metallized films can play a critical role in the function of products such as mylar balloons to reduce how easy it is for helium to escape back into the atmosphere. These coatings are also found on the reflectors of your car headlights in order to light your path on a late night drive. And they're also found in solar blankets and spacesuits to protect against harsh solar rays. You can even find metallized films in many food packaging products to improve the cooking process in a microwave oven. Metallurgical films are any film that improves some base metal's properties. In many cases, the thin film is deposited by sputtering or evaporation with an ionized reactive gas. These are often thin film coatings of titanium nitride, which provide an aesthetically pleasing gold color while being also non-toxic and very durable. And these coatings allow coated parts to last up to 5 times longer when compared to an uncoated part, thanks to the titanium nitride being very wear resistant. Metallurgical films are commonly found on drill bits, milling cutters, punches, engine valves, jewelry, and medical implants. And there are even wear resistant coatings on ball bearings and gears that make them last longer, and that even includes the ball bearing of your ballpoint pen. An electroluminescent film is a film that converts electricity into visible light. The most common example of these would be light-emitting diodes, called LEDs, and organic light-emitting diodes, called OLEDs. The OLED layer is often situated between 2 electrodes. One is a cathode and the other is an anode. And for TVs, laptops, smartphones, and tablets, and even LED lighting, only one electrode must be transparent so you can see the image on that side. OLED technology does have an advantage over LED for 3 key reasons, all of which stem off the LED's display requirement of a backlight and how an OLED display does not require a backlight. Thanks to the lack of a backlight, OLED displays are able to be transparent optionally if we make the cathode and the anode transparent. And OLED displays can also be much thinner than LED displays, which allows for the production of flexible displays. OLED also allows for us to have some of the higher contrast color than you would if there was a backlight, so you can get more of a true black compared to an LED display. There are 2 key thin films that are used for energy, either for energy production or energy storage. Energy production uses some form of a photovoltaic thin film to convert light into energy. Photovoltaic films make this conversion by having electrons move from one layer to another layer when UV light strikes the film. By having electrons move through the layers in one direction, the film can be used as a little energy engine that uses light as fuel. Common photovoltaic thin films include cadmium telluride, SIGs, and perovskites. Perovskite is becoming a more attractive photovoltaic thin film as it's very efficient and it can be additionally coated to be non-toxic. Thin films are also found in thin film batteries, such as the ones being used on electric vehicles. In these cases, thin film batteries allow for a energy dense alternative with a small format and a lighter option compared to alternatives. Last but not least, we have semiconductor films. These films are most commonly produced with CVD and ALD applications, but QCMs are still used in several of these applications. For thin film transistors, or TFTs, hafnium oxide and cadmium selenide must be sputtered onto the substrate. TFTs are found in active matrix pixel addressing, which is in active matrix OLEDs or AMOLED displays. There are also magnetic sensors comprised of indium antimonide, indium arsenide, and gallium arsenide. Magnetic sensors are found in smartphones for use as a compass and in currency detection products like vending machines. There are even micro electromechanical systems known as MEMS that make things like electrometers that are found in your smartphones and drones. QCM still remains a valuable product for research and development of semiconductors and are appearing in more production tools in the form of semi-QCM sensors. Okay, let's review some of the key takeaways from this webinar. There are 2 key categories for thin film applications: PVD, and CVD. There are many types of thin films used in common household products that you are now aware of. And lastly, thin film applications benefit from using a QCM for in situ measurements. A QCM ensures a high quality product and reduces how many products must be scrapped due to an incorrect or inconsistent thin film thickness. We hope to see you at some of our upcoming events. The first one that we have upcoming is going to be the SVC TechCon on Long Beach, California, May 3rd and May 4th. And Sheldon and I will be exhibitors at that booth, and we look forward to meeting you in person. If you have any questions that come up after this webinar, please feel free to contact us at reachus@inficon.com, or you can also contact Jennifer Reeks for QCM monitor and controller questions, as well as Paul Grimshaw on QCM sensor and crystal questions. Now, without further delay, let's see if there are any questions.
Thank you, Chris. So we have a few questions. The first one is, how accurate is a QCM?
So how accurate is a QCM? That's going to depend on the thickness resolution of the controller that you're using. The crystal itself doesn't have too many limitations on it. So ultimately that's going to depend on the frequency resolution of your controller and how fine a resolution the controller can provide rate and thickness information for. So our standard is going to be plus or minus 0.03 hertz, which is going to get you definitely towards like a 0.0 or 0.3 angstrom per second kind of range. And that would also be like a 0.03 angstrom thickness resolution. But we do also have some products out there. A great example would be like IC6 or the IMM200. That's going to give you 10 times that resolution for both frequency, rate, and thickness.
And the other question is, isn't the thickness on the QCM different than the substrate?
That's a good question. So the answer is yes. The thickness on the QCM is most definitely going to be a little different than the substrate, unless the crystal was the substrate. But we have something called tooling factor built into all of our monitors and controllers that would help compensate for that. Tooling factor is going to scale up the thickness and rate on the QCM so that it matches the thickness and rate on the substrate. So once that's been set up properly for your chamber based on where your sensor is in relation to the source and the substrate, then they will match, or rather the controller will give thickness and rate that matches the substrate.
Another question, what is a typical vacuum pressure for resistive heating?
Okay, so resistive heating, as with a lot of the PVD applications as a whole, they're going to need what's called a high vacuum instead of ultra high vacuum for MBE. So high vacuum is more like 10 to the negative 6 to 10 to the negative 6 to 10 to the negative 10 torr. And of course, ultra high vacuum was 10 to the negative 10 to the 10 to the negative 12 torr. And I guess it's worth also then mentioning CVD and ALD applications, they tend to be more towards like the millitorr range to a few torr in range. So those ones are much higher in pressure.
Thank you, Chris. Another question on slide 10, it looked like there was another controller. What instrument is on slide 10?
That's a good question. So slide 10 is showing a product that is currently in development. That is the IMC 300. That product is to be released later this year. And hopefully everyone gets to see that when it's released and gets to see what it's able to do. It's going to be doing stuff very similar to like what an XTC3 and an SQC 310 does if you're familiar with those products of ours.
Okay, and one comment, I use a single sensor for MBE. Why would I need a rotary sensor?
Okay, so I guess first I'll just start with a rotary sensor is just going to give you more uptime overall. A single sensor is more prone to failing earlier than a rotary sensor because a rotary sensor could hold between 6 and 12 crystals versus 1. So the main goal would be uptime. However, if you're using a single sensor for MBE, if it's on like the edge, you may be able to use it for an extended period. And on the edge, I mean the edge of the spray of material. But you need to keep in mind, if you're on the edge of the spray of material, you might not get as consistent a deposition rate on the crystal, and you're also going to see a lot less material on the crystal compared to the substrate. So you'll need a very large tooling factor there.
Okay, and one last question. How thick of a layer can you put on a crystal before the crystal needs to be replaced?
That's a fun one. So ultimately, the answer is it depends. And the reason for that is each crystal, they behave the same way for the same application, but each application is going to use different materials, which have different densities. And we're also going to be doing different stacks of materials, which the way the layer on layer reacts or acts with each other can be different. And ultimately, the crystal will continue to oscillate until there's enough material on it that ceases its oscillation in the thickness shear mode, which is in this direction on top of the crystal here. And as you add materials, certain ones might be what we call high stress. So a great example for that would be your optical coatings tend to fit into that category. A lot of your oxide materials and nitride materials fit into that category. And high stress means we've got either some additional compressive or tensile stresses that are being applied by that material on the crystal that is making it more difficult for the crystal to oscillate. So the thickness can vary for those factors alone, but then there's also tooling. So your tooling is also going to make it so the crystal might last longer or shorter because we are kind of scaling things. We're scaling thickness that's being reported compared to what's actually happening to the crystal. So if you had a very large tooling factor, the crystal might not last as long as if you had, or I misspoke, if you had a very low tooling factor, the crystal might not last as long as if you had a very high tooling factor. But of course, you don't want to use tooling factor to try to get longer life, if you will. You're really going more for what's on the substrate. So it really does depend. Sorry that there's no more specific answer there.
Thank you, Chris. I don't see any more questions. So if there's anyone out there that does have another question that comes to mind, feel free to reach out to us. And we thank all of our viewers for attending, and we hope to see you in the future. Thank you.
All right. Thanks, everyone. Bye now.